In this video, we're going to talk about elementary matrices and how they relate to row operations. So we talked about the n by n identity matrix yesterday in class, but just to remind you again, the general entry of the n by n identity matrix has ones down the diagonal and zeros everywhere else that's not on the diagonal. So here we see examples of I2, I4, IN. Again, we notice that we see ones down the diagonal, zeros everywhere else. The whole point of this identity matrix is so that we can have an identity with respect to matrix multiplication. So if you have an n by p matrix A or an m by n matrix B, then if I multiply on the left by in for A, I get A back again. If I multiply on the right by in for B, I get B back again. And we did this proof yesterday in class. We know that the ij entry in in of A is the summation as we go across the row of the ith row of the identity matrix and down the jth column. Try again. We go across the ith row and down the jth column, write out the summation. Pardon me. The only one that's not zero is this one that's here. That EII is 1. Everywhere else we have a 0. So if we do the simplification, we just get a sub ij. So we really do see that the general entry of I times A really just does give us the general entry of A back again. And again, like I said, we did that in class yesterday. So let's talk about elementary matrices. An elementary matrix has to be square, but it's a matrix that results from taking exactly one elementary row operation on an identity matrix. So remember, our elementary row operations again are swap two rows, multiply a row by a non-zero constant, multiply a row by a non-zero constant, add it to a second row, replace the second row. So to give you some examples here, this first one, E1, is an elementary matrix because rows 1 and 2 have been swapped. E2 here is an elementary matrix because row 3 has been multiplied by 5. And E3 here is an elementary matrix because we've taken -4 times row 2, added it to row 1, and replaced row 1. Notice these are all one elementary row operation away from an identity matrix. So the reason why we like elementary matrices is that the effect of multiplying on the left by an elementary matrix has the same exact effect as doing the corresponding elementary row operation. So what that means is, if I go back up here, if I took a 3 by whatever matrix and multiplied on the left by E1, the result would be swapping the two rows in that matrix we multiplied by. Likewise, if I took a 4 by whatever matrix and multiplied it by E2, the result would be taking that matrix that we multiplied by and multiplying the third row by 5. So here's an example with what looks like the row operation for multiplying a row by a non-zero constant and adding it to a second row. Here, let's look at this elementary matrix. We've taken row 2, multiplied it by 3, and added it to row 3. And we're going to take this and multiply it by the A matrix. Notice that your first row will be unchanged because when I match up this 1, 0, 0 and flip it and match it up with this row here as I go across the columns, I get the same thing back again. Same thing with row 2. If I take it and match it up with each of the columns, I'll get row 2 back again. If I take row 3 and match it up with each of the columns, notice it takes 3 times everything in row 2, adds 1 times everything in row 3. And that's what we end up with in row 3. So we really do see that corresponding row operation here. So what this means for us is that we can actually do Gaussian elimination, row reduction things by doing matrix multiplication. Okay. So, pardon me. So again, we notice that the only row that gets changed when we do that one elementary row operation is the row that we're replacing. And the only entry in that row is that's changed in that row is the one that's in column K. So what I mean by that is, we're taking the identity matrix. It's a lot of words and I stumbled over them, I apologize. But we're taking the identity matrix, we're just trying to write what a general elementary matrix looks like of that last type of elementary row operation. Here's what our general matrix looks like. Here's row K, column K. If I want to take row K and multiply it by C and add it to row L, the only change that gets made is that I will take this 0 out of row L, column K, and replace it with a C. Okay? So what that means is that the general entry of this elementary this matrix looks like a 1 down the diagonal, zeros everywhere else, unless we are in row L and column K, and in that case, f sub Lk is C. So what we're going to do here is show that that row operation that we did really does do what we say it did. This is just a proof of that result. So if I do E times A, where that E is the previous matrix, okay, so I remember I called those elements F. When we do E times A, the general entry looks like I go across the row, the ith row of E, down the jth column of A, and do that corresponding product and add them up. Here's that just written out longhand. Okay, so we're in the row we're not in the lth row. That's what I'm saying here. If we're not in the lth row, then everything else except for the diagonal entry is a 0. The diagonal entry is a 1, so what we're left with is a sub ij. So what this tells me is that if we are not in the lth row, then the matrix multiplication doesn't change the row. The general entry is the same as what it was in A, which is exactly what we expect when we do that type of row operation. What happens in row L? Just write it out longhand again. I'm going to split it into two pieces. We have the LK term and the LL term. So this is row L. LK term, LL term. So the LK we said was C. The LL term is 1. Every other term is a 0. So we get the entry looks like C times AKJ plus ALJ. So what that means is we've taken C times row K, added it to row L. This is exactly what we would expect to see when we do the corresponding row operation. So this last part here was just a proof that multiplication by that elementary matrix does the exact same thing as the corresponding row operation. In this case, the row operation where we do a non-zero constant times a row and add it to a second row. The reason why we want to do this is because we are going to be talking about how to find inverses of matrices with a general algorithm. We need to make everything precise because when we talk about inverses of matrices, I got to be able to talk about undoing matrix multiplication. So we'll talk about this in class about how we do that with elementary matrices.